Acids and bases are actually probably one of the more important topics that we could be discussing. If you take AP chemistry, and again, if you're right with the chemistry gods, you'll be doing that. We will spend close to a month and a half talking about acids and bases. In here, we're not spending a month and a half. We're actually just introducing acids and bases, which are probably one of the more important concepts that you could ever deal with in chemistry and in your own personal life. A lot of the foods and a lot of the drinks that we actually intake have an acidic value to it. In other words, there's a lot of things that you eat and drink, and then your body has to regulate those types of things. So it's not necessarily something that we can just blow off, but it is really important. So, and the things that I'm teaching you in here are super easy. We don't even get into the stuff that we talk about in AP. So this is some easy concepts, and especially the things that we're doing today. Acids and bases, and I hope that you've had some type of acid and base knowledge or education in junior high, hopefully. And again, it's just going to feed off of that. So when we talk about acids and bases, all of these things are ionic solids. So we're still working with ionic compounds, except now we're focusing on the hydrogen ions and the hydroxide ions associated with these acids and bases. All of these dissolve in water. There are some that are better at dissolving in water than others. We'll talk about that, I don't think today, but we'll get to that. Let's see, there's some fun stuff there. Some characteristics associated with acids. All acids conduct electricity. All acids taste sour. Now, what I don't want you to do is go and grab a bottle of hydrochloric acid and say, I wonder if Mr. Craig's right, and if hydrochloric acid tastes sour. Well, that's not necessarily the acid you want to try to take. But we do have a lot of acidic things that we do partake in, like orange juice, lemon juice. Those do taste sour. Let's see here. We don't use litmus paper in here, but if you were to dip some litmus paper, maybe back in junior high or whatever in elementary school, and you had litmus paper, the acid would change to a red color. We will have a demo, not necessarily today or even tomorrow or the next time that we meet, but we'll be using an indicator. An indicator helps us to tell when we're at our desired pH. And what's cool about an indicator is it stays clear until it hits that desired pH, and then it'll change the color. The indicator I'll be using in here is a hot pink color. In other words, it stays clear, I mean there's no color, and then when we get to about a pH of 7, 7.5, it goes from this clear solution to a hot pink. And then if I pour some more acid back into it, it disappears and it goes clear again. So that's what an indicator helps us to do, is it's something that actually is produced once we hit a desired pH. Some common examples of acids, which you're probably familiar with: acetic acid, citric acid. Acetic acid. Anybody know where you partake in acetic acid? Yeah, it's vinegar. It's things that you put in your salad dressing. Hopefully you know about hydrochloric acid, sulfuric acid, kind of nasty. Bases are a little bit different than acids. These taste bitter. They also conduct electricity. Now, if you've ever had your mouth washed out with soap, you had your mouth washed out with a base, so it does taste kind of bitter. So hopefully you haven't had to experience that in your life, because you're good kids. You're good kids. You don't talk bad to your parents. You don't use them nasty words. Also, soap feels slippery when wet, of course. Also, we use bases to neutralize acids, which is nice. And if you had litmus paper, it would change it to a color of blue instead of red. Some common examples: sodium hydroxide, potassium hydroxide. Probably the one that you're most familiar with is ammonia in your everyday experiences. All right, so that's a real quick introduction. There are two theories that we're going to talk about. We'll actually talk about both of the theories today. Hopefully this first theory, the Arrhenius Theory, is the type that you talked about when you were in junior high or wherever you learned about acids and bases initially. And the theory states that if you have an acid, when placed in water, it actually forms these hydrogen ions, also known as a proton. In other words, it's a hydrogen atom with the electron gone, so it has just a +1 charge. If you have a substance that produces that, you're looking at an Arrhenius acid. If you're looking at an Arrhenius base, then you have something that might look like this, and it produces hydroxide ions. So if it produces OH, then we're looking at an Arrhenius base. So it's kind of neat because some of the acids don't even have an OH within them, but they produce OH. That we'll talk about in AP. I know, got you excited now. Don't go running to guidance and signing up for AP just because of that little tease right there. We can also, when we talk about hydrogen ions, we can also mention that, I'm sorry, not a plus sign, but an equal sign there, that these two things represent the same thing, because whenever you introduce hydrogen ions into a solution of pure water, the hydrogen will attach itself to the water molecule and form H3O with a +1 charge. Now, if you write it like that, or write it like that, I'm going to be able to sleep tonight. So it's the same thing. So this is actually the way that I was taught, and then when I got into college, that's where they went. So both of those are acceptable. All right, so here's some examples. I just gave you that one. That's an Arrhenius acid. That's an Arrhenius base. Isn't that exciting? Oh, yeah. All right, and then there was the second theory called Bronsted-Lowry. And Bronsted-Lowry is the type of theory that you really want to know, because it's all about who's donating that hydrogen ion and who's accepting that hydrogen ion. So there'll be somebody that gives, and then if somebody gives it, somebody's got to take it. So if we're talking about a Bronsted-Lowry acid, it's the thing that is giving the hydrogen ion away. If it's a Bronsted-Lowry base, it's the thing that's accepting that hydrogen ion. Okay. We'll have some examples here. Did everybody get those two blanks there? Donor, acceptor. And then it kind of just said that. So here's an example of one of those. And we'll talk about conjugate acids, conjugate bases. Oh, you're going to love it. I'm telling you. The acid-base lecture in material is probably the funnest of them all. Yeah, I can't lie about that. When we talk about conjugates, keep in mind that when you see conjugate, that's always on the product side, or the right-hand side. If I see acid and base all by itself, it's always on the side that we start with, or the reactant side, or in your perspective, the left side. So conjugates just simply tell you where it's at, whether it's on the product side or the reactant side. If it's an acid, it still does the same thing, whether it's conjugate acid or regular acid. So acids donate hydrogen ions. So if you were to look at, say, the before and after, and this is how we want to analyze a question like this. We have how many hydrogens in this molecule? 3. How many in that one? 2. So if we come over here and we go from NH3 to NH4, what's happened is a hydrogen ion from the water was given to the ammonium. That's why the water in this case is acting like an acid, because it's donating a hydrogen to the NH3 who's accepting it. Now if we look on this side, and actually this should be a double arrow. Does your notes only have a single arrow on there?
Yep.
Oh, you need to fix that right now. Oof. So what does it mean if the arrow goes both ways? It can go both ways. Very good. So that means that these guys will form this, and then it'll flip around and form the other stuff. Dang, isn't that cool? It's called a reversible reaction. The bad news is the reversible reactions, that's the majority of the reactions that actually exist in the universe. Okay? And we're not even talking about equilibrium, but that's even more significant. But save that for AP. All right, so if we're going in this direction, how many hydrogens do we have here? And we go to 3, so that means in the reverse direction, the NH4 is acting as a acid. But since it's on the product side, we call that a conjugate acid. And the OH is accepting that hydrogen, therefore we call that a base. Isn't that cool? So it's always the switch of one hydrogen. Here it has 3, there it has 4. Going back, now it has 4, now it has 3. I had to give it away. And I like to draw the arrows just to help me see or visualize what's actually taking place there. But again, remember, conjugates are on the right-hand side. There's another example. So let's do some practice problems. So taking a look at this problem, the question wants you to determine, it says determine the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. Here's how you attack this type of problem. So you look, because I'm not telling you what these things are. You have to look at the before and after situation. This is the before, this is the after. All right, so H3PO4. Now, you don't know the name of that yet. How many hydrogens does H3PO4 have? 3. How many do we have over here? 2. You need to focus on, because a lot of you are going to ask, how do you know which one to look at? Look at your non-metals. So the PO4 is here, the PO4 is here. That's not going to change. The hydrogen count will change. So if we go from 3 to 2 hydrogens, who is donating, or I'm sorry, is the H3PO4 donating a hydrogen or accepting one?
Donating.
Donating. It's giving one away. How do we know? Because we go from 3 to 2. So what that means is it's donating a hydrogen, which means that H3PO4 is a acid. Very good. Now, that's great. If this is an acid, then this has to be a base. But let's find out why it's a base. How many hydrogens do we have on the HOH?
2.
How many do we have on H3O+?
3.
So that means it gained a hydrogen from the acid. Make sense? Okay. And going in the reverse direction, okay. So again, you have your 2 hydrogens here going to 3. So did this gain or lose a hydrogen? Or accepted? Accepted or donated? It accepted. Where did it accept it from? Well, there's only these 2 guys to work from this side. So if H2PO4 is accepting a hydrogen, this is acting as a acid or base. A base, but since it's on the product side, we call it a conjugate base.
Can you label them like BA, BB, and CB, and CA?
That's what I'm doing right now. Yeah.
Oh, okay.
So in that case, H3O+ would be a
Acid.
conjugate acid. Very good. So again, how do I know that? Because I have 3 hydrogens here. I donate one of them. Now conjugates are on the product side. Regular acid and bases are on the left side.
So the acid is like the quarterback, and the base is like the wide receiver.
Yes.
So the hydrogen is like the football that gets tossed back and forth.
Good analogy. I like that. We're going to keep that on there. Let's look at another one here. Okay. So NH3, again, what we're looking at is we're looking for similarities. So there's no nitrogen here, no nitrogen here. So we want to focus on the compound that has nitrogen. How many hydrogens do we have in NH3? 3. How many hydrogens do we have here? 4. So this is acting as a base. Very good. Okay. The reason why it's acting as a base is because it is gaining or accepting a hydrogen from here to here. Okay. So if this is accepting, we're going to call that a base. Now water is acting like a what? An acid in this case. However, back here water acted as a what?
Base.
Oh. Water can act as either an acid or a base. Interesting. There's a term for that, but you're not required to know it, but it's called amphoteric. Something that can act as either an acid or a base. We have 4 hydrogens here, we have 3 here. So what did NH4 with a +1 charge do to go from 4 to 3? Donated. Very good. Okay. Therefore, the NH4 with the +1 charge is acting as an acid, but since it's on the product side, conjugate acid. Very good. And then the OH is conjugate base. Doesn't that make sense?
Yes.
All right. Here is extra practice. Okay? Now this is not in your notes. This is not in your notes. This is extra. So let's take a look at this one. If you want to write it down, that's fine. If you just want to look, that's fine. Again, you want to focus on the SO4 because when you go from this side to the other side, is SO4 here? No, I moved it over here. Look at that. What a guy, I'm telling. Just remember that the plus sign just means and. So let's look at the before and after. How many hydrogens do we have? How many hydrogens on the H2SO4? So what did the HSO4 do? It accepted a hydrogen. So the HSO4 or the bisulfate is a base. And the H3O plus is a, you got it. And then, so to go from 2 to 1, does this need to donate? Now, here's what some of you are doing. I know you. Some of you are like, oh, the arrows, they're always going either opposite or the same. In other words, in toward each other or away from each other. Just be careful. That's why you want to look and not automatically go, oh, that one's got 1, that one's got 1. Don't do that either. Okay. Look for the non-metal for each and then compare them. Okay. So looking over here, what is the water in this case? Conjugate base. And the sulfuric acid is a conjugate acid. Isn't that nice?
Mr. Craig, for number 2,
Yeah.
was NH4 the CB or CA?
The CA in this case, because we have 4 hydrogens here, it had to give 1 away to get back to 3 hydrogens. Yes, Connor?
From what you said before with the arrows, how else would it go?
Well, it could go opposite each direction, going in toward each other. I mean, what I don't want you to do is key on the arrows. In other words, find a pattern. There won't be a pattern. Always look at the actual compounds. Okay. All right, here's some more practice that's a little bit different than what we had in the first set. And I'll give you the ones here in a second. So this question asks, the following substances act as a Bronsted-Lowry acid in water. So this thing here is a what? An acid. How do you know? Because it says so. It says it's an acid. So, and if it's in water, what can we write next to this?
H2O.
There you go. Look at that.
I think it's H2O.
Okay? Actually, I'll just write it as. That's okay. You can do it either way. Okay? So if the bicarbonate, or HCO3, is an acid, what is the water?
Base.
Base. Very good. So if this is the acid and that's the base, what is the bicarbonate doing? Donating a hydrogen. Very good. Now again, I'm not requiring you to draw the arrow, but if you need to, it is a nice visual to be able to see what's going on, then you may. Then looking on the other side, how is this going to look? HCO3 with the -1 on the other side.
CO for -1.
So it'll be no hydrogen, right? So CO3, what's the charge going to be?
-1.
-1? What's -1 here?
-2.
-2?
Yes.
Okay, so how did you do that?
It's a poly.
Well, here's how you do it. You actually say, okay, well, this has a -1 charge. I'm losing a +1 charge, right? So I'm giving away the hydrogen. So I'm already -1. I'm losing another +1. So that equals -2, right?
If it's a poly, should it just add what the poly is?
Negatives.
That'll work.
Alright, well that's all I'm gonna do.
Okay? So the CO3, and that's one of your 10 polys anyway. You know that carbonate's -2. Psh. And let's see here. What's the other product here? So we add a hydrogen to the water. You're making what now?
H3O.
H3O, and what's the charge?
-1.
Okay, so here we have no charge. We're gaining a +1 charge. So again, 0 plus a +1 equals +1.
But it doesn't balance.
Doesn't balance?
Yeah.
What do you mean it doesn't balance?
The charges don't balance.
Okay, enlighten me. What do you mean by they don't
No
balance?
one cares.
And actually, Connor brings up a pretty good point. The charges have to balance on both sides, correct? Oh yeah, yeah. They have to. They must. So let's look at this.
We can't, negative 2 plus 1 equals rule breaker down.
No rule breakers here. So negative 2 plus 1 equals what?
Negative 1.
Negative 1. So 0 plus negative 1 equals?
Negative 1.
Good point, Connor.
Oh,
Hey.
good job. That makes sense.
All right. So, okay, now let's finish this guy. So CO3 has how many hydrogens? 0. Ooh, here we have 1. So how's it going to get a hydrogen?
Just one from the...
There you go. So the CO3 is acting as a
Conjugate base.
conjugate base. Very good. And the H3O plus is a
Conjugate acid.
conjugate acid. All right. One more. Okay. Last example. Now you're going to love this. I promise. Here, this is acting as a base. Oh my goodness. Wait a minute. Didn't we just say it was an acid here?
Let's put CO2.
Now hold on. So we said that this is acting like an acid, and this is acting like a base, so that must be what? Amphoteric. Very good. Somebody paying attention.
Amphoteric?
Amphoteric.
Where is that?
That's not in your notes. That's an AP term. I'm just throwing that out there for, that's your bonus.
How do you spell it? How do you spell it?
Amphoteric.
That almost looks like an
Okay. So amphoteric means that it can act as either an acid or a base. Better terms, it can donate a hydrogen or accept a hydrogen. So if this is acting as a base, and it's in water, all right, so here we go. If that's acting as a base, water's acting like a what in this problem? An acid.
So that's ampho.
Okay, water's also amphoteric. Very good. We got 2 amphoteric substances here. But in this case, this is acting like a base and this is acting like an acid. So which way's the arrow going to go?
Both ways.
It's going to be H2CO3.
Come on, you know who the acid is.
To the
Okay.
base.
So in that case, if I'm telling you, and especially if I am giving you an amphoteric substance, I have to tell you what it's behaving as. Or there'll be some very subtle clues, like back here, do I have an amphoteric? Yeah, this could be an amphoteric substance here, but this one is not. So I'd have to give you some insight to help you decide whether it's an acid or a base. I'm always here to help. That's right. All right, so on the product side, what are we going to have here?
H2CO3. And
Very good. And put the hydrogens on the front. So H2CO3, what else?
hydroxide.
Hydroxide, good. And what's the charge on hydroxide? -1. Okay. And let's finish this guy off. So what is H2CO3 acting as?
Conjugate acid.
Conjugate acid. This is also known as carbonic acid. You'll learn about that later on this week. And so if it's an acid,
Gives it to the conjugate base.
so this is a conjugate base.
Why is it a carbonic? Because it has carbonated?
Carbonate, yep. So you get rid of the 8 and put an ick on it. Dang, I just gave the lecture away.
Wow.
Okay? All right, so here are the ones. The 1s and the 2s are your homework.